Aloha, Internet. This is your captain speaking, Lester Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary. This is From First Principles. We are back with 3 great research papers we're going to cover this week, starting off with a new laser plasma device that could be light enough to be used in the field. We'll be going to Egypt for this story out of Lawrence Berkeley National Labs that was published in the Physical Review Accelerators and Beams. We're going to muon from that story to our second story about sodium batteries. Are they finally cheaper than lithium batteries and just as powerful? This is a new paper out of University of Chicago and UC San Diego that was published in the paper Joule, just Joule, a cell press journal. And we will wrap up with a trip down memory lane to one of my favorite cartoons of all time, which is Kim Possible, as we talk about how naked mole rats might be the key to having a long life. This is a longevity study. This is out of Tongji University in Shanghai, China, that was published in China. This is From First Principles. Let's get after it. My friend.
How's it going?
How are you?
Well, we're done with Nobel Prize weeks.
Yes, we are back now to breaking news after several weeks of just insane coverage.
Dodgers are...
Oh, the Dodgers, yes.
Back in the World Series.
Because we're in LA.
Because LA. I have my Joe Kelly shirt on.
I was going to say, I think we have now witnessed the greatest single performance, as every announcer has said over the last couple of days, in baseball history by Shohei Ohtani. Yeah. In that last game against the Brewers.
Yeah, I wouldn't really know because I'm a true Dodgers fan and LA native, so I didn't start caring until they qualified or whatever for the World Series. So I honestly have no idea who they're even playing or anything. I don't even know if Joe Kelly is still on the roster, if that's how you say it. But anyways, now that we're in the World Series, dude, I'm a huge Dodgers fan.
Classic.
I love the Dodgers.
This is exactly why everyone hates Dodgers fans. We're very excited. I think the World Series starts when our next episode will come out.
Yeah.
So we will be donned in Dodgers memorabilia on the pod. And we're going to start with, as a hard pivot. On our first story, which is about this new laser plasma device. And so the headline on this story is Directional Muon-beam shows potential for advanced imaging technique. Researchers at ATAP have developed a compact source of high energy co-limited muons. Collimated muons using a laser plasma accelerator, potentially enabling advanced imaging technologies. Now, what's so interesting about this is it appears that this is going to be relevant for the field of archaeology, especially.
Yes.
Again, this is out of Lawrence Berkeley National Lab and was published in the Physical Review, Accelerators and Beams. So what is the top line on this paper?
Yeah, the basic idea is in order to make muons, usually you need extremely large particle accelerators. Okay. And these guys have done it in effectively the size of a lab, maybe a big lab, but it's still not the size of CERN or SLAC, where it's hundreds and hundreds of meters worth of stuff to create a muon beam. And that becomes really, really relevant if you're trying to use muons to do CAT scans on very large things. For example, the pyramids or a volcano. And so that's sort of the stuff we're going to get into.
Got it. Okay.
But to prime this understanding, we need to first understand what is a muon. Okay. So a muon is a central part of the standard model of particle physics. It is one of the fundamental particles that is kind of like a heavy cousin to the electron. Okay. A heavy cousin. Now, one of the mysteries of particle physics is that particles come in 3 generations, okay? There's the electron, which is a class of leptons, and then there's this thing called the muon, and then the tau. You might have heard. You're smiling because
it just makes me think of Pokemon.
yeah. But well, it's exactly that. And actually, it's one of the big mysteries that is still unsolved today.
Okay.
Why it comes in these 3 generations. But in any case, that's the universe that we live in. This muon is exactly like the electron, except it's 200 times as massive as the electron. So here we've got a photo of the particle, all of the particles that make up the standard model. This is everything that we are made out of. Not just the mass, but also all of the energy that we're made out of. The light, the photons are part of the standard model. The stuff that is massive, like the up and down quarks, those are the stuff that make protons and neutrons. The electron together makes atoms. So all of these things are fundamental to our universe. Mm-hmm. And yet, what we're most familiar with is up and down quarks and electrons, right? Those are the stuff that make atoms. And then photons and obviously stuff like that. But in terms of stuff that have mass, muons are this elusive kind of particle. They're quite rare. And they're rare because they're really unstable. They have a mean lifetime of about 2.2 microseconds compared to an electron, which is extremely stable, right? And they were first observed in these things called cosmic ray showers, which are these showers that come when a cosmic ray hits the Earth's atmosphere. A cosmic ray is a really highly energetic, massive particle. Maybe it's like a giant atomic nucleus. Obviously, that's small, but like, you know, in terms of like particles, it's quite big. When these things come from wherever, galaxies, supernovae, whatever, and they come and they hit our Earth's atmosphere from high up, they release a shower of particles because they interact with a bunch of particles in the Earth's atmosphere. And part of that shower goes from kaons and pions. Those things then disintegrate into muons, and then that's what we usually see. That's where we usually see muons.
Is this related to the, you know, when folks have the charts of the sun having these large solar bursts and then it reaches Earth's atmosphere and everyone's like, that's what's going to kill the grid? Is that this a similar concept as these cosmic rays, or it's a different
No, I mean, it's similar in the sense that it's a massive gust of charged particles from our sun that is so massive in flux that it starts messing with our electrical grid. Cosmic rays, on the other hand, are very, very sporadic. They're rare. They come from all over the cosmos, so they're not like pointed from one direction.
Yes.
When the sun releases a flare, all of those charged particles come all at the same time, and then they completely overwhelm the electrical environment of the Earth.
That makes
right?
sense.
With cosmic rays, they're once upon a time, they come in and then they have these showers, right? And what you can do is you can have detectors all over the Earth that catch the particles that come in, and then based on the geographic layout of all of the detectors and the timing of when each detector went off, you can be like, oh, it came from that direction, right? Because if it came from that direction, then that detector would go off first, the one that's closest to that angle, and then the one that's further would go further. So it's sort of a way that we've used, muons are a way that we've used to map out cosmic rays, right? And they've been coming at us for forever, okay? They're ubiquitous, they're harmless. The flux is really weak. It's about 1 a minute through your fingernail. Okay. Like right now, as we're sitting here, there's about 1 muon a minute coming through our fingernail. These things don't really interact all that much because they're so heavy. They'll just like go right through, right? So historically, it's just been like something that's been nice to know about the universe, that we've got this particle, right? That's the second generation.
It's sort of, it's not pop music, it's niche underground. When you're digging in the crates, it's cool. But.
Yeah, it's cool. And it's got some really cool like implications in fundamental physics research. Like for example, you can make a hydrogen atom, but instead of an electron, you can stick a muon around it, because the muon also has a negative charge, right? And so, but the muon is 200 times more massive.
Right.
So what that means is the size of that muonic hydrogen atom is going to be way, way smaller, which means you can now start probing effects of the nucleus. Like you can start asking questions like, how big is the proton? Right? With a normal hydrogen atom, the electron cloud is so big that the size of the proton doesn't really matter. But if you start shrinking the size of the hydrogen atom, this is one of the ways that in fundamental physics, people start trying to figure out what is the size of the proton. They use muonic hydrogen. So it's like, it's the twin of the electron, but it's just like big.
Makes
okay.
sense.
That seems to be the only thing that is different about it.
It's big,
okay.
big bro.
Yeah, exactly. And you know, it's been a nice quirk up until the 1960s, okay? In the 1960s, there was a guy, Luis Alvarez. He was a Nobel laureate. He was actually played by Alex Wolff in the Oppenheimer movie.
Right.
Right. Who's a very famous actor. Luis Alvarez, he was in the Oppenheimer movie, he was a PhD student of Lawrence, who was making the first cyclotron in Berkeley. And Alvarez was the guy who read the discovery of nuclear fission, and he replicated the experiment, and he was all excited. Well, when he got older, he started. He was a great experimental physicist, okay, and he started realizing that what you could do is you could use a muon the same way that we use X-rays in medical imaging. Okay, the principle of X-rays in medical imaging is you have an X-ray source, you have a detector on the back, right, and then the X-ray is going to penetrate through soft tissue because there's not a lot of stuff that's like there. But the denser stuff, like your bone, it's not going to be able to penetrate, and that's going to create a shadow. So then you can image an entire skeleton
On the
using
detector.
X-rays, right? Now, the same principle we can use now for very, very large things, because the muon is kind of like an X-ray in that the path that it takes, how far it gets through something, is dependent on the density of the stuff that it's going through. Okay, fundamentally, it's most of particle physics is that. Okay, it's like, so it's going through, and because it's this massive cousin to the electron, it doesn't actually interact that much with matter, and so it can go through a lot more stuff before it gets stopped. Okay, so now you can start imaging things like buildings or volcanoes, or in the case of Luis Alvarez, in the 1960s, he imaged the Pyramid of Khafre in Giza, which is the second pyramid. Okay, there's three big pyramids in Giza. The second pyramid, the one that still has its cap on, that's the one that he imaged. He actually took a muon detector to the inside of that pyramid, put it there for like about 2 years, and you know, the flux, again, as I was saying, from these cosmic rays are really, really small. So you got to wait a really long time to get a nice statistical signal to be like, is there, and the question he was trying to answer was, is there a cavity inside the Pyramid of Khafre? Okay, is there like a hidden chamber? We're always worried about
all the secrets.
Yeah, all the secrets, right? We're always worried about hidden chambers. It was a negative result, actually, because he didn't find any hidden chambers in the Pyramid of Khafre.
This is interesting. This was happening in the 60s.
In the 60s, yes.
This is quite some time ago.
Yeah.
And I imagine Luis Alvarez, if he saw what they're doing at the pyramids now, I don't know if you get these videos on TikTok of DJs with these massive light shows in front of the pyramids of Giza.
I've seen those.
It looks like they're mapping muons with the amount of just, lasers that are going. I obviously that's not what's going on.
No, it's like visualizing his experiment somehow.
Right.
It's pretty cool.
Anyway.
Yeah. So he didn't find anything, right?
Right.
But that sort of started this idea of we can actually do something with muons and do a kind of muon tomography. It's kind of like a CAT scan, where what you can do is take a scan with muons in this direction, and then a scan with muons in this direction, in all these different directions, map out the shadows, and then from that reconstruct the physical 3D nature of whatever is inside.
So this was sort of this understanding that we can use, muon detectors as a means by which to do mapping of large objects or spaces.
Yes, large objects, right? And actually, in modern times, there's been a renaissance. There's been this program called the ScanPyramids. In 2015, they actually used it to map out the Great Pyramid of Giza, which is the Pyramid of Khufu, I believe. That's the biggest of the three. And they actually did find a void there. They found a previously unknown void. It was at least 30 meters long above the Grand Gallery. And there you see the muons are coming in from cosmic rays. And you're basically waiting for these muons to come in. And from each direction, you can map out how many muons came in from each direction. And you can say, oh, actually more muons came in from this middle part of the pyramid than from the outside, which means that middle part of the pyramid must have some kind of cavity or hole where the muons had no problem getting through. Does that make sense?
It does. It does.
So it's like there's a hole.
Yes.
There's a hole in there. And they actually found it. But it highlighted a limitation of the approach.
Okay.
Which is that you got to wait months to years to actually scan this stuff. Because the flux from the cosmic rays is so low. Okay? Now, this has applications elsewhere as well. Okay? It's not just like, okay, archaeology, is there a hole in the pyramids that I can go find gold or whatever?
There's a lot of people who are very curious about what's underneath the pyramids.
A lot of people care a lot about that. But I imagine that people living around volcanoes care a lot about whether there's a hole in their volcano, right, where the magma could come out. And so they've actually used these detectors on volcanoes, like Mount Vesuvius, Mount Etna, Stromboli. All three of those are in Italy. You also have Sakurajima, which is in Japan. And what they've done is using this muon tomography, they've mapped out the internal density of that volcano to see where the magma chambers are, where there's maybe less pressure. So if there's like an eruption, which way would it go? You know, because it would go to the path of least resistance through this like lower pressure part. So it reveals these like lava plugs, magma conduits. Again, though, there's a limitation. Because we are relying on cosmic rays, which the flux is so low, you're only going to get a static image. You need a year to take this photograph. You need a year to take this CAT scan. And then once you have the year, you have a static image of where the volcano is. But it would be really nice if we had so much flux, right, that I could get like a moving picture of what is happening inside the volcano using muon tomography.
So until this day, what we have is we've discovered a methodology by which to map large objects, look inside of large objects such as the pyramids or volcanoes. But two of the primary limitations have been it takes a really long time to get a static, not motion image of these things because the frequency by which muons pass through them is so very, 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 very low.
Exactly.
Right? Okay, so that's the foundation of where the story now picks up from.
Exactly. And now we pick up with this paper. Okay, this paper came out in the Physical Review Accelerators and Beams. It was a team at the Bella Center at Lawrence Berkeley National Lab. They used the laser plasma accelerator. Okay, and they did something very cool, which is they used a beam. They used an apparatus that's only about a meter big to create a very, very powerful muon beam. Okay, and in order to do that, they did a kind of physics that is very akin to wakeboarding. Have you ever gone wakeboarding?
So I've only gone once, and I immediately almost got a concussion the first time I got up because I just fell and slammed my face into the water.
Yeah, this is why I never go into water. So I have never gone wakeboarding, nor will I ever go wakeboarding. But wakeboarding is a very useful analogy for the physics that's going on here because it's quite incredible, right? Usually to make muons, you need a massive particle accelerator, and that massive particle accelerator then bombs into like something, and then that something, the interaction of all of the highly energetic particles with whatever target is going to create your muons. That's usually how you do it. Here, they've created an electron gun, effectively, that is extremely fast, very, very high energy electron guns, with a short rifle in some sense. And what they're doing is wakeboarding the electrons, okay? So here's what's going on. In wakeboarding, right? What you're doing is the boat goes at a really high speed, and then you got a surfer that surfs the waves of the wake that the boat makes, right? And you don't even need like a rope to tether you to the boat. I think there's a photo of Mark Zuckerberg just like with an American flag, right? You know that one? Yeah. So like, you know, you don't need you can just, the waves themselves have enough structure and energy.
Right.
You can stand on top of those and then just go, right?
Yes.
And you can ride that energy.
Yes.
That's what they're doing. That's what they're making the electrons do that. So what they do is they've got an ultra short laser pulse, okay? And they're going to fire it into a gas. It's hydrogen doped with nitrogen. Okay. And what this,
I just want to say, hydrogen doped with a little nitrogen is such a funny sentence.
yeah. I guess it's used a lot in like chemistry for like semiconductors. Doped meaning like you're removing some other stuff and you're putting some other stuff in.
Yep.
Yeah. And so what that's going to do is that laser is going to go in and it's going to create a plasma, because the laser is going to push out a bunch of the negative charges, and you're going to get free electrons, and you're going to get these positive nuclei. Now, all of a sudden, you have a bubble of positive charge, okay? And then if some straggly electrons get trapped in that bubble, they're going to ride that bubble, and because it's positively charged, they're going to want to get the hell out of there. And so you're going to push these electrons out.
Yes.
And they're going to be accelerated by these powerful electric fields. And you can get somewhere like several billion electron volts, like giga electron volts, in a 30 centimeter plasma channel.
That's crazy.
Okay. And versus like, usually that takes hundreds of meters of traditional accelerators. Like SLAC does this, and SLAC requires like a massive thing that goes under the freeway. And, you know, so this is really cool that they're able to do this.
So
okay.
the part of the insight here is this miniaturization of being able to create these electron beam, these particle beams at like a very, very small scale, but still retaining
the energy
level.
Exactly. Yeah.
Which is obviously meaningful, because that means you can have smaller footprint of the accelerator.
That's the key. That's the key.
Idea.
And this is a relatively new technology, laser plasma accelerators. Okay. And they're still sort of coming into their being. They're still quite big. But the fact that, you know, we're getting to these high energies,
right,
and it's not like hundreds of meters, is a very promising step. Okay, so that's the first step. You got now an electron beam. Okay, a massive, really highly energetic electron beam. Now what you're going to do is you're going to dump that beam into a giant block of lead, steel, and concrete. Okay, and what that's going to do is the electrons are then going to interact with these heavy nuclei. Lead is a very heavy nucleus, right? And as it interacts, the electrons are going to slow down, and they're going to slow down, creating radiation. Because remember, we've talked about this a lot. If a charged particle accelerates or deaccelerates, it's going to release energy.
Yes.
Right? The only time somehow that it doesn't do this is in the confines of an atom, right? Because that's when
stuff gets weird.
Yeah, all the rules are off. But if it's a free electron and it's moving, and it starts accelerating or deaccelerating or changing direction, it's going to create this thing called Bremsstrahlung. It's a German word for breaking radiation. Okay? So all of that energy of the electron is going into high energy photons. These are gamma rays. And now those high energy photons will interact with the atomic nuclei to create pairs of particles. Pair production is something that happens when you got a bunch of energy in one spot, and that energy spontaneously splits into two particles, one that is the matter part, one that is the antimatter part. You get the matter-antimatter pair. And if the physics is right, then you're going to get a bunch of matter-antimatter pairs that are exactly muons and antimuons. Okay? If you tune the energy such that the energy is exactly E divided by C squared, the mass, remember E equals mc squared, right? So if the energy is exactly equal to the mass of two muons, one muon and one antimuon, then the energy is going to dump into muons and antimuons. That field is going to take over, and you're going to get a muon and an antimuon. And so what this ends up being is you get a collimated meaning it's all in one direction. That's where that word from the headline came from.
Yes.
All in one direction. It's directional, and it's a muon beam.
Yes.
Okay?
Yes.
So now we've got a muon beam. Very cool.
Right. From starting from this electron beam, that now we put through this lead, steel, concrete substrate, and it had this pair production that has now resulted in this, matter antimatter
muon
pair.
Yes, exactly.
Okay.
Yeah. So now
Yes.
we got a muon beam all of a sudden.
Yes.
Right?
Yes.
Well, okay, you say it's a muon beam. How do you know it's a muon beam? Because everyone else is going to be like, how do you know it's a muon beam? How do you know it's not some other random particle? How do you know it's just not just another electron, right? So now you got to do the work of actually showing that it is a muon beam. So the detection system looks like this. This is the measurement room. We've got the laser coming in from the left, then the laser creates this electron beam. The electron beam gets bombarded into this about 3 meters worth of lead, steel, and concrete. And on the other side is your detector. And that detector is what's going to catch the strays, catch these muon strays that are coming in. Okay? How do we make sure that the particles that are coming out are muons?
Yes.
Okay? I thought this was really cool because this is like a very simple test. Okay, here's what they did. They said, okay, well, we know from all of the years of work on muons.
Because we've been doing this since the 60s.
Yeah, we know about muons for a while, right? Yeah. And we know that their decay, their half-life is 2.2 microseconds, right? So if we can characterize the half-life of these particles that are coming out and it's exactly 2.2 microseconds, then we're good to go. And that's exactly what they did. They collected data from 760 laser shots over 2 hours. So that's about 5 per minute. And then what they did was they triggered on the giant amount of electrons that would come out. And then they would look for a second signal, which is from when the muon would decay. Okay, because the electrons are coming out first, and then the muon would decay, and it would fit this exact exponential. They did a histogram. They fit an exponential to that histogram, and the exponential decay curve had a time constant that was exactly 2.24 microseconds, right? So it's like a telltale sign.
Yeah,
you can't ignore that, like, because this exponential decay thing, that's something that you learn about in undergrad physics, right?
Yep.
It's like at the end of the day, like it just took like a nice undergrad graph.
Yes.
To be like, yeah, that's a muon.
And so what's so interesting is it's not, with a lot of these stories, you not only have to create the new thing, right? In this case, how can we do muon generation at a smaller scale than like several building size accelerator?
Yeah.
But then everyone's going to say, well, how do you know you generated muons?
Yeah.
And so you also need to have a detection system on the tail end to validate your generator.
And not just detection, but like, how do you analyze that data to make sure that like you can convince everybody out there who's trying to say you didn't do it, right? Because there's so many people that are trying to do this, right? And everyone wants to get there first, so you got to really check your work. So that was really cool, right? So now they finally found they finally made this muon source, right? And now this gets over that cosmic ray limitation because now instead of a drizzle,
right.
If I could now make this such that I can point it somewhere, I don't have this drizzle of cosmic rays. Now I can just have a fire hose that's like aimed at whatever thing I wanna look at.
Yes.
Right.
Yes.
And the natural muon flux is something like, as I was saying, it's like one particle per square centimeter per minute, right? That's one particle through my fingernail per minute. This thing is going to be 40 times as much, okay? And this is the LPA source. That's what it looks like. It's just kind of a tabletop looking experiment. I mean, obviously there's a bunch of stuff in the building that is supporting this tabletop experiment. So it's not so trivial to put this in the back of a truck or something like that. But at the end of the day, it's from this laser plasma source.
Yes.
And even at 1 hertz, it's going to be 40 times the particle delivery rate of cosmic rays, right? And it's an order of magnitude reduction in exposure time. Now you can start doing the same kind of muon tomography of your pyramid or whatever, but instead of taking like years, it's going to take maybe a few days. Right?
Which is like, for anyone who's trying to do any of these aspects of archaeology, geology, these things where you want to look at these massive structures, that time efficiency is, I mean, incredibly meaningful. It reminds me very much of like the time efficiency of having like the Vera Rubin Sky Observatory.
Exactly.
It's the same kind of thing where it's like you're having more frequent, high quality data that's just becoming available because of this fundamental understanding.
And it's only the beginning, right? Because like like these lasers now, they're going to get much better. Right now, these guys are doing like the top this thing can shoot the electron beam at is about 1 hertz, right? But we could be getting to kilohertz, which is thousands of shots a second, right? And then that's another 3 orders of magnitude above what we already have. And so now you can start doing, okay, instead of a few days, now you got a few minutes. Right. We can, and then now that becomes really crucial. Suppose we think a volcanic eruption is happening.
Exactly.
We can go there and we can monitor the volcano every minute and look at the internal dynamics, right? Yes. And be like, okay, we need to evacuate now, or maybe we got a few more weeks.
That's actually a really practical, real world use case for this, basically as close to real time detection system that you can imagine. Extrapolating this, if you increase that source from 1 hertz up, and then you can also miniaturize the rest of the supporting infrastructure to some sufficiently small thing, which can be, it could be multiple 18-wheeler trucks. Like that's still crazy.
Yeah, man, right? It could be like multiple 18-wheeler trucks that you then like you put it somewhere and then you assemble together.
Right.
Like that's still crazy. That was not possible. You couldn't do that with a massive detector. Now you could possibly do that in the next few years if things progress the way that they are, right? There's a lot of cool applications that I was reading about.
Yes.
That weren't completely obvious to me.
Okay.
But then once I read them, it was like, oh, that's cool.
Okay.
Yeah, that's cool. So one of them is obviously like archaeology reimagined, right? You can now do targeted excavation.
Yes.
You can like point your muon beam at specific spots, and when you're excavating, you don't want to do like a brute force approach and just excavate everything. You've got limited time. You don't want to disturb the excavation in some sense. So you can like target and try to get to whatever cavity that you're trying to go to. You can also start imaging smaller objects like sarcophagi or like statues, things like that. You just stick that right in front of your muon detector. Real-time volcanology is something that we talked about. You can do near real-time observation of density changes like magma movement, gas pressure, lava plugs.
For the like Yellowstone super volcano that always comes up, I mean, it'll be huge for that. Because we would be able to know.
Yeah, we'd be able to know, and that'd be really nice.
That'd be really nice.
That'd be really nice to know. There's also national security.
Okay.
And infrastructure, something I thought you would like.
Yeah.
So the speed of this muon tomography would be such that now we can scan cargo at the ports without opening the box, right? Because you can't do that with X-rays. The metal is too thick, right? But you could just stick a muon thing, and then it's gonna. So routine inspection of these shipping containers can happen in minutes now. You don't,
Yeah.
So then you don't have to trust the shipping manifest. You can literally be like, okay, is there something there? If there's any nuclear smuggling that's going on, nuclear waste and nuclear like rods and things like that are very dense.
Right.
They're going to interact with muons in very weird ways because that's just nuclear physics, right? So now all of a sudden you can have like safeguards and waste management, things like that. The other thing that was cool was civil engineering, right? Because like our infrastructure, let's face it, is quite old and needs repair.
Yes.
And you could take these muon beams to bridges and dams and buildings, and they could reveal hidden cracks, water infiltration, catastrophic failure. So it's a whole new mode of. It's like we've unlocked a new type of light,
right?
In some sense, right? We've unlocked a new type of imaging,
right? No, exactly. We what's so interesting about this? I mean, the NatSec implications got my gears turning. I mean, it becomes very difficult to basically smuggle a dirty bomb anywhere.
Yeah.
Particularly, you can put these on any number of source platforms.
Yeah.
But the civil engineering one, I think, is so particularly for where this is true globally, but especially in the U.S., where we have now legacy infrastructure that is beginning to. The 405 has been shut down to one lane multiple weeks in a row.
Yeah, that's been the bane of my existence, dude.
And like deciding how, like what civil engineering projects are most pressing by having an actual data set that is not necessarily just time or, citizen complaints, but has like a data set. And again, this
we can like we can X-ray concrete,
right?
Yeah. Like that's what it is. We can now X-ray concrete and stone,
I can imagine. I mean, imagine putting this on a. This is getting a little ahead of the skis here, but you could have some sort of drone platform that you can then have and then do surveys local. Just in terms of being able to distribute this to like lower cost use cases. I mean, muography in that context would have huge impacts.
Yeah. The only problem I'm thinking with the drone stuff is like because you need a detector.
Yeah.
Like with drones, it's really nice with radar because light bounces back. Muons don't bounce back.
You need the thing on the other side.
Yeah, exactly.
To be able to.
Yeah, that's
to
like, even in X-rays, right? Like they always they put like a thingy.
Yep.
When they do the X-ray.
No, that's fair.
Yeah.
That's a very important distinction. Does not negate any of the actual benefits that we just talked about.
No,
which are meaningful. And so I guess the key advancements here that are sort of that are the next steps are higher energy beams, miniaturization.
Yeah.
Those are the two key areas for improvement.
Yeah. Those are the two key areas, and like the fact that this part has been solved, which is like making muons with a high energy electron beam, that part's been solved. Now the problem is miniaturization of it and making it higher power, right? Like making the hertz faster, the repetitive nature of that laser faster. Right now the laser like shoots and then it's got to recharge and then shoot again, right? But if you can make it rapid fire,
if you make it semi-automatic,
yep, exactly,
it becomes very interesting. It's fascinating.
Very cool.
I don't want to.
That was a cool one.
That's a really cool one. I don't want to muon from that story too soon. I know that's a double of the same joke. However, we're going to move to our next story that's coming out of University of Chicago and UC San Diego about sodium batteries that are finally catching up. And they're cheaper than lithium and just as powerful. And this is out of Joule. And because we all have devices.
Yeah.
We're all very familiar with the limitations of battery technology.
Yes.
And everyone talks about innovation and things are getting better. But one of the jokes everyone always says is, well, why can't my iPhone or my Samsung Galaxy, blah, 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 last a week?
Mm-hmm.
Why is it only 20 hours?
Yeah.
And so what is the top line for, I didn't even know that sodium batteries were like a competing platform to lithium.
Yeah. They're not.
Okay, they're not.
We don't have enough fundamental science to do it. This is in that line.
Okay.
Yeah.
Okay.
This is getting there.
Okay.
This is trying to get us there.
Okay.
The idea is that we want to, this is from University of Chicago and UC San Diego. They're trying to create a sodium-based battery because that is just going to be way chiller than lithium-based battery, okay?
Yes.
Lithium has all sorts of problems. We're going to get into it. Before we get into it, let's talk about batteries.
Okay.
In general, how does a battery work? Okay, so a battery basically provides a electromotive force, okay? It is converting chemical energy into electrical energy. It's highly efficient compared to converting like a generator or a turbine, which converts mechanical energy into heat, which then becomes electrical energy and so on and so forth. So batteries function by converting that stored chemical energy into electrical energy, right? And the way they work is they've got two electrodes, okay? They've got one part, which is called the anode, and that's the part that releases electrons. Those electrons then go through the circuit to the cathode, which is the other part of the battery. That's why, when you have the Duracell, right? You've got one part that's positive and one part that's negative. You connect that to wires, you light up the light bulb. What's happening is there's some chemical reaction that's going on inside of that battery that is pushing electrons one way and sucking electrons the other way. And because the electrons have to go through the circuit in order to complete that path, they have no choice but to go through whatever load you're trying to put on it. In some cases, it's a light bulb. And so they go through the light bulb, they expend some power, and then they go back, okay? And that's effectively what a battery does. Now, the main question is, why doesn't the electron just go through the battery? Mm-hmm. Why does it have to go through all the way around the circuit? Why can't it just go through the battery to the cathode, right? From the anode to the cathode. Mm-hmm. And that's where the electrolyte comes in, okay? There's something inside the battery that is preventing electrons from going through. It only lets positive ions go through, okay? So at the anode side, and this happens during discharging, okay? So in discharging, the battery's providing power, okay? The anode, which is the positive terminal, the anode is the negative terminal. The negative terminal releases electrons that go through the circuit, and the positive ions go through the electrolyte to the cathode, okay? And and that electrolyte blocks electrons, so the electrons have no choice but to go through the circuit. Okay, that's the key. And then what you want to do is you want to be able to charge it again, right? And so when we charge it, we're just reversing this entire process. So now the cathode releases electrons, the positive side releases, because what the power, the external power that you just supplied does is it's reversing this chemical reaction. So now the electrons travel the other way and the positive ions travel the other way, and then you're resetting this, scale.
Yes.
Where now all of the chemical energy is back into the system.
It's like a seesaw.
Yes, it's exactly like a seesaw where you had chemical energy and that became electrical energy, and now you're providing work back to convert from electrical energy back to chemical energy, right? And to do this, lithium has basically won the race so far.
It's the Usain Bolt of...
Yes, lithium ions are the Usain Bolt because they are fast. Why are they fast? Well, they're super light, right? It's number 3 on the periodic table. That means that the nuclei are only 6 atomic units big, 3 electrons, 3 protons, 3 electrons, actually sometimes 4, but in any case, very small. It's the lightest metal, and because it's the lightest metal and it only has 3 electrons, right? So the inner 2 electrons are in the stable, nice shell, right? The inner shell, the helium shell, and that outer electron is just ready to get the hell out of there, right? And so it's super willing to be negative. It's super willing to be an ion. It's got this high gravimetric energy density, which basically because it's low mass, right? The lower the mass, but you still have one charge.
Yes. So
very high density in that sense. High electrochemical potential, which means that you can reach high voltage and high energy density, right?
Yes.
So all of these things make it a really good ion for batteries because it has no problem moving around in the electrolyte. Right? And then just donating that electron to go into the circuit.
That makes sense.
Makes sense, right?
Yes.
The problem is it is super scarce. Okay? In the universe, it's super scarce. Since the price has been up like 700% since 2021. It's only like 0.0017% of the Earth's crust. It's in concentrated deposits in like the lithium triangle. I forget what are the actual countries. I think it's like Chile, Bolivia, in South America, that's the big lithium triangle, and then also Australia has a bunch of lithium.
It's funny, in Zimbabwe, which we talked about, is where my family's from. We just actually discovered like the 4th largest lithium deposit on Earth, and it's now created interesting geopolitical implications because of what you're talking about, because of that scarcity and its importance for all lithium battery powered things, which is basically everything. It's a little complicated.
Yeah, here comes colonialism, part 2, disguised as capitalism. But yeah. So obviously, it's got problems, right? And there's 2 ways to mine lithium, which I'm sure Zimbabwe is going to learn soon.
Yes.
One of them is hard rock mining. This is super energy intensive, open pits, land degradation, looks really bad, and 15 tons of CO2 per ton of lithium.
This is what the Chinese are already out there doing.
Oh, already. Okay, great. Yeah. And then there's brine extraction, which is like brine is like the stuff you get in these saltwater lakes high up, where all of the minerals from the mountains come in, and then you basically mix it with water and you evaporate it. Okay? And it requires 500,000 liters of water per ton of lithium, depletes the water, contaminates the soil, contaminates the groundwater. Everyone hates it. So lithium kind of sucks.
It accomplishes the job, but no one likes working with it.
Yeah. And it's like, it's really good at its job. I get that. Okay. Like it's light. It's number 3 on the periodic table. It's like theoretically the best thing because like you wouldn't use hydrogen. Hydrogen is its own thing, but lithium is the lightest metal, right? So it makes sense, but there's problems, right? So why would we want to use sodium? Well, I just told you, right? Lithium sucks. Sodium is the heir apparent, right? It's right below lithium on the periodic table. So lithium is number 3. Sodium is number 9? 9 or 11? Wait, 1, 2 plus 6. No, it's number 11. It's number 11. Anyways, it's way bigger than lithium, which is at number 3.
Yes.
Okay. But it's right below the lithium on the periodic table. And if you remember from your high school chemistry, everything that's in the same column on the periodic table has very similar chemical properties. So all of the stuff that we were doing with lithium, we could just do it with sodium, right?
Yes.
Because it's the same,
Yes.
just bigger.
Bigger. Okay.
Right? Obviously, there's going to be problems with it being bigger, but the good things about sodium outweigh the bad. Okay, it's the 6th most common element. It's 1,000 times more abundant than lithium. It's like it's in salt, right? NaCl.
Yes.
Sodium chloride is salt. So you can extract it from rock salt. You can extract it out of the ocean. Sodium carbonate is like super cheap compared to lithium carbonate. The only problem is it's big. Okay, it's like way bigger. It's significantly larger. It's like 0.3 angstroms greater atomic radius, and it's got 3 times the mass, right? And what that does is it's going to cause problems if we just substitute the sodium instead of lithium into our already existing technology.
You can't just hot swap.
Yeah,
it.
you can't just hot swap it because this thing is bigger and it's heavier, right? Lithium right now, what it does is the way that we use lithium is we've got the anode and the cathode. The anode is made out of something called graphite,
Yes.
which is a carbon compound. It's the stuff that you're finding in lead, and the graphite is actually what like holds your lithium ions. And I think photo number 8 shows that. You've got on the left just layers and layers of graphite that hold your lithium ions, and then when the lithium donates an electron into the circuit, it moves into the cathode, which is this lithium MO2 layer, right? If I just do a hot swap from lithium to sodium, that sodium is going to cause mechanical stress on the electrodes because it's bigger.
Right.
Like those layers of graphite are now going to start
being a little bendy.
and they're going to break, and that's going to create rapid degradation, a short cycle life, right? You're not going to be able to recharge it as many times as you want.
So like life cycle, long-term lifespan.
Also
becomes
exactly, because every time you're charging and recharging and charging and recharging, that layer of graphite is getting populated with lithium, and then the lithium goes away, and then it gets populated with lithium, and the lithium goes away. And just like any other thing, like the movement of stuff in and out of the pages of your book, right, is gonna cause degradation. So that's one problem.
Yes.
The other problem is inherently there's gonna be a lower energy density, right? Because this thing is bigger.
Yes.
So for 3 times the mass,
Yes.
I have the same amount of charge.
Yeah.
Obviously, the energy density is going to be lower,
Yeah,
right?
that makes sense.
It's going to be a heavier battery if I want the same kind of charge. And the theoretical energy density is at least 30% lower in comparable lithium systems. It's also kinetically, it's very sluggish. The larger nuclei means that the sodium is going to move slower in the battery itself, right? The power that you're getting out of a battery is limited by how fast the lithium can go from one end to the other, right? But if you've got a larger thingy, then that thing's going to move slower, and so my total power output is going to be lower, right? There are all of these problems.
So despite its abundance, because it's heavier, it makes it less energy dense, which means you have to have a bigger battery to do the same level of output. It's going to be slower, so you're going to actually get less ultimate power out of it as well because it's slower. It's not just that it's heavier, it's also slower. And all of this means that the efficiency of a similarly sized sodium battery system as compared to a lithium ion system is just going to be inefficient.
Exactly.
And we've gotten used to our iPhones being a certain size.
Exactly. And so all of these problems are persisting, right? That doesn't mean that sodium could still not be valuable. Okay? Because fine, maybe not for the iPhone. Okay? But battery has a lot more usage than just our electronics. For example, if you've thought about stationary battery power, right? If you've got like a giant electrical grid and you want to store a bunch of power for when the electrical grid goes bad, or if you're trying to do renewables, right? And you have a giant solar panel array, but now it's like cloudy, you want to be able to store all of the sunlight from when it was actually sunny to then use when it's cloudy, right? All of these stationary storage parts, it doesn't really matter if it's bigger.
Right.
Right?
Yeah,
if it's cheaper, that's what matters.
That's actually
right?
a really good point. Yeah.
Right? And that's why people are excited about sodium.
Okay.
Right?
That makes sense.
It could pave the way for like a truly green future where, you know, we don't need to rely on these like fossil fuels and coal and things like that. We could be a completely green economy, and we just store like power from wind, power from solar, power from all other things for whenever there's a rainy day, right? If we can make that really cheap, then we've solved that problem of like allocating those resources from when the energy was coming in to when the energy is actually needed.
Because one of the biggest limiting factors right now is that battery storage for its level of capacity and efficiency is just way too expensive.
Yes.
To distribute
and like
scale.
not as good.
And not as good.
Yeah.
But that's
we might be getting there with this kind of stuff, right? And so this is where the paper comes in. This is a paper in Joule by Jin An Sam Oh and Professor Ying Shirley Meng's team. This is out of China. Oh no! This is, what am I saying? This is, I'm confusing the next.
Oh, our next story.
Our next story. This is out of UC San Diego and University of Chicago. They created a novel solid-state electrolyte with unprecedented performance, okay? And this is solid-state electrolyte that can shuttle silicon, okay? So what they did was, in the lab, they created a battery out of a crystalline phase of sodium, boron, and hydrogen. Okay, it's referred to as ONBH, orthorhombic crystal. It's got orthorhombic crystal symmetry, so it's the solid state compound, and it's got these cage-like anions that have this really nice crystal symmetry. And the way that they created this was very cool, because what they did was they combined two substances. There was a boron and hydrogen, BH4, and then there was a sodium, boron, and hydrogen, which was two sodiums, a bunch of borons, a bunch of hydrogens. The two of them together create this sort of metastable compound. A metastable compound means it's got like this phase that is stable, but only so-so. You kick it in some direction, you like heat it up, you like do something to it, it goes off and it does something else, right? And so you want to like, it's like really like finicky, okay? And you want to sort of freeze it in this nice active state without getting to the inactive state, right? So what they use something called quenching, which it's kind of like, you know, if you've ever like in the top ramen restaurants when they try to make soft-boiled eggs,
yes,
you want to stop the cooking,
yes,
at the exact moment. So you put it in ice.
Yes.
Right? You boil the egg for like 6 minutes, and then you put it in ice to stop the cooking. That's what they did here. They got their substance, they heated it up, and then they quenched it very quickly, and it stayed in that stable sort of high energy situation. And that was really cool.
Even though they cooled down.
Even though they had cooled down to room temperature, they had done it fast enough. Right? That like the physics of it had sort of stayed where they wanted it to stay.
Yep.
Yeah.
That's really, which is like, just like talk to the egg, the example you just talked about.
Yeah. It's something that we talked about during the Nobel Prize chemistry stuff.
Yeah,
it's like chemistry is a lot like cooking and baking.
Yes.
Those are the techniques that you use, right? But you got to be very good at it, right? And that's precise. The magic. That's the magic of chemistry. So this new compound was very nice because, you know, one of the problems I was talking about was how sodium is bigger.
Yes.
So it's got a hard time going through the electrolyte from one electrode to the other, right?
Yes.
And the faster that we can make this thing happen, the more power we can get out of our battery and the more energy efficient we can make our battery. Well, this particular electrolyte, that's a solid state electrolyte, what it did was it's got this paddle wheel effect. Okay, what's happening is the large crystals of boron and hydrogen, they can actually start spinning in their state, and that spin shuttles sodium.
Oh, yeah.
Kind of like a paddle wheel.
Yeah.
You know?
Yeah.
Yeah, it's really cool.
That's actually really
so you
interesting.
create these super highways for ion hopping, right? The other thing that's cool about this is there's a really high density of unoccupied sites. So you have this like very nice highway where the sodium can go, and then you have this spinning effect on all of the stuff around you that is creating a kind of momentum push that is like jiggling all these sodium atoms to go through, right? And now you can have this superionic conductivity. The entire population of actively conducting sodium ions.
Yes.
And then the substrate itself sort of shakes loose any ions that got like stuck somewhere.
Yeah.
You know?
So it's creating some lubrication for this flow.
Yes, exactly. Yeah, and it's really cool because now you've got you've got a way to move forward, right? With sodium batteries, right? The other cool thing that I thought was very cool is this thing can handle low temperatures. Okay. One of the problems that I think you've heard about probably, right?
Yes.
It's like Teslas.
It's hard to drive a Tesla in Canada.
Yeah.
In the winter.
Yeah, because the lithium ion batteries just like totally fail.
Right.
Because at that low temperature, there's not enough motility.
It's true for all electric vehicles, not just Tesla.
Yes. Okay. Please don't sue us. But they're like at low temperatures, these lithium ion batteries are not performing that well. Well, as a combination of this solid state chemistry that's happening and like these spinning thingies, the motility of the sodium ions, this thing can actually have pretty good performance at 0 degrees Celsius.
That's really interesting. So despite its negative aspects because of the size of sodium as compared to lithium, which creates lower energy density and slower movement through the circuit. At low temperatures, there's with this sort of new lubricant, that's the electrolyte that's facilitating the movement. The sodium battery can actually perform more efficient at lower temperatures as compared to lithium
than the current lithium ion batteries.
That's very interesting.
So this is already like actually, and so now it becomes suitable for like EVs in cold climates.
Right.
If you want grid storage, without a lot of like thermal management.
Yes.
Like I'm sure Scandinavia and Norway
would love something like
this, right? Where it's like they're frozen like half the year. Or whatever.
Or wherever they put the seed bank where they have all the seeds and it's buried below the ice. You can imagine a huge sodium battery store that
that like powers that and like make sure that that's okay.
Or the neutrino detector in
Antarctica. Ice cube.
Ice cube.
Yeah. So we're far away from building like a full battery.
Yes.
But the architecture is there.
Yes.
And they actually did make a battery. It's not like commercially viable, but it's like in their thingy, and that's the Teslas on Fox News. Oh, they got stranded.
Yeah, because of the which is so funny. I remember I've had an electric car for a while. I remember like, you can't drive in the cold weather, and I'm like, well, in LA, it's not that bad.
Yeah, in LA, in California, it's like pretty nice.
It's pretty nice.
Yeah, but in terms of the battery that they made. So they made this thing with the solid electrolyte, and they used a tin alloy for the anode, and they used a sodium chromium oxygen composite for the cathode. It retained 80% of its initial capacity after 100 cycles. Pretty good.
It's pretty good.
It's not commercial grade, right? Commercial grade goes to like thousands of cycles.
Sure.
But an average coulombic efficiency of 99.8 to 99.9, which means it's a stable system. There's not that many side reactions going on.
Yep.
The sodium isn't going off and doing something else. It's really getting recycled every time, And there's a lot of broad implications to this kind of stuff because, one can imagine you can like totally start reshaping the grid around a capability like this, right? If you have a way to create a battery that's 100 times cheaper than lithium, right? And it's going to be crucial for gigawatt hour scale batteries, right? And it's all solid state. There's no flammable liquids. So it's inherently safer if you want to make building sized versions of this.
Don't let the AI overlords get a handle on this.
Yeah.
Because I mean, that's a big aspect we've talked about with AI is the power generation issue. And it's not only the generation, but also storage as it relates to that. It's both problem sets.
It's both problem sets. And now we can make it cheaper. So I wonder, right? Like, is this maybe gonna make that better? Is it gonna make it worse? I'm not sure.
It would be interesting to see if there's capital that starts to move, because I know that new battery technology is a buzzword that constantly gets brought up in venture capital, meet cutes and all this stuff. And so when you have like Signal, this is Signal, does that create now sort of this arisal of a couple of these hardware upstarts that are trying to take the funnel of VC cash money and try to operationalize it more quickly? I'm not saying that that's feasible, but we've seen it in other areas that are interesting, where once someone has sort of identified that there's some minimum viability, because of the importance of power to what is viewed as this great power battle on AI, you're seeing private capital move earlier in the cycle of research to insert themselves in order both to accelerate it and control it earlier in that process.
I mean, I wouldn't be surprised if the grad student who's the first author in this gets hired by Tesla or Rivian or someone.
Right.
No, exactly. I'm going to be honest. We know people who did exactly that, okay? You know who you are if you're listening to this. So the other, as you were saying, like in terms of like, now that something like this is possible, people like moving towards that capability, even in electric motility, right? In electric vehicles, this isn't just because it's like a little bit, it's not as energy efficient as lithium, because it never can be. Lithium is just the gold standard. It's got 3 instead of 11 thingies. You can still, the fact that it's going to be cheaper to make these kinds of batteries is going to be huge for places in the developing world, right? If it's cheaper, that's what matters over there, right? People they don't really care about the environment. They're trying to get from A to B,
right?
And like they want a car, right? Totally, I can totally understand. I've been there. So it's like, if you have this lower upfront cost, that could accelerate adoption.
Yes.
You could also have these things called hybrid battery packs, right? Where it's like you can combine the lithium ion and the sodium ion, right? So if it's like super cold, you can have your sodium ion battery turn up,
right?
Heat up the car, and then the lithium ion battery like comes up. So it's not like moot, right? There's a lot of there's a lot of good points here.
The hybrid battery pack was my initial thought, and I totally agree with you on the, whether you want to call it short range EV, urban EVs, but for I can imagine, right, like where my grandmother is now, in Yanga and Zim, having things that are lower cost. The cycle issue is not relevant, right? If it can do the job that it's needed to do efficiently and at a reasonable size scale, it will have huge implications for a variety of developing economies, which don't have the luxury of we'll be having to worry about the environment.
Yeah,
we didn't have to worry about the environment during our industrial revolution.
No.
Why does everyone else need to?
Yeah, exactly.
X, Y, and Z. And so, very interesting.
Yeah. And then there's obviously the geopolitical aspect to it, right? Which is like China's making all the batteries. The extraction of lithium comes from very few countries that might turn sour on us. So if we can make it out of sodium, that'd be pretty nice.
That'd be pretty nice.
Yeah.
I already know we've lost the battle in Zim, and that's unfortunate, because I was begging the U.S. ambassador to Zimbabwe to pay attention about what was happening there, and we needed that anyway. Very, very interesting. And so scaling this to like gigafactory level, like there's a path.
Yeah.
Okay.
Yeah. It's like, you got to optimize the entire cell design for cost and manufacturability and all this other kind of stuff. But it's not going to be like sodium or lithium. It's like sodium and lithium.
Yeah, it's
going to be both.
Yeah.
But the global energy demand is 100% going to exceed
Oh yeah.
the amount of lithium we have on planet Earth,
Yes,
right? Even
yes.
if we took off every bit of lithium, as developing countries become developed, right? As the billions of people want more and more power, as they rightfully should, right? Like if we live like this in America, everybody else wants to live like this too. They want ACs, they want cars, they want mobile phones, blah blah blah. So having the sodium ion as a battery pack is a critical step.
It makes total. I mean, this is you can't have infinite growth in a finite system.
Yeah.
And it's sort of trying to continue to address that. Like, look, I'm not anti-capitalism, but like, you literally can't have infinite growth in a finite system.
Yeah.
So, like, what's the plan?
What's the plan here? Yeah. And innovation seems to be the one thing. I mean, obviously, I think we're also gonna get to a point where we're gonna seriously start thinking about sustainability. And again, sodium battery is a path towards that, right? If we could be completely reliant on renewable resources, which are transient, that seems to be one of the biggest problems. Transient and they're far away. Well, if we have really nice batteries that can store stuff around everywhere, it'd be pretty nice.
And there's clearly the land mass. I mean, you could take the massive swaths of California, make them massive battery facilities, sodium battery facilities, power the whole U.S. or North America just with we don't need to disrupt normal human living and
just stick it in the middle of nowhere
and then just pipe it. Or again, because it's so cheap, you can create the cheap thing that you can have at home and you just it's disposable.
Well, piping it is hard because we lose a lot of power
on the pipe.
Yeah, but just have a bunch, everywhere,
because it's so cheap.
So
it doesn't matter. This is a great moment after we've talked about batteries and all of the fundamental science that powers them. Talk about our sponsor, Standard Model.
Standard Model beverages.
On every episode, you see this beautiful agave soda here with us. Tasty, refreshing, just 4 ingredients. It is a creation of 2 masterminds, one of which is our resident PhD.
Yes, I'm one of the founders of Standard Model Beverages, named after the Standard Model of particle physics. My co-founder was a friend of mine from UCLA physics PhD. He used to work at CERN as an experimental particle physicist, got really into making amazing drinks over the COVID-19 lockdown. And we started this company because for the same reason that we sort of started this podcast. We love science, we love science communication, and we love celebrating the heroes of science. So on every single bottle on the back, you're going to find a biography of one of our favorite scientists. The soda itself is fantastic, I gotta say. This one is guava. We've also got mango, made from agave sugars, water, and botanicals, and fruit juice. Just that's it. Nothing else. Really, really good. And you can go on our website and you can read a little bit about the quantum mechanics of our design, what this hole and this wave means, and what this wave function means here. Again, standardmodelbevs.com. You can get your own. We ship all over the United States, and we are available in certain locations in Venice, California, and the Bay Area. Check out our website, standardmodelbevs.com.
If you're looking to support the show, check out Standard Model. And as we get increased demand, we can make it more available in your local grocery and other retail stores. And again, the support for the pod has been incredible. We are going to continue with our core format, which is, again, looking at and talking about core science and research stories from first principles, which brings us to our last story of the day, which is about a naked mole rat aging research. Now, for those of you who may not know, Kim Possible, the Disney Channel cartoon.
I used to love that show.
It's one of my favorite cartoons of all time.
We used to get that in India, too.
That's how good it was. That's how good it was. Global. Yeah. Not only is it one of my personal favorites, so when you sent me the show notes, I was like, oh, we're going to talk about Rufus. The do ringtone to Call Me, Beat Me, Kim Possible is my literal SMS ringtone currently right now on my iPhone 16 Pro Max.
Dude, that's how much triggered like so many childhood memories when you did that. It's like, you know that's so Raven when like the camera goes into her eye. That's what just happened.
Same exact thing. So this is a longevity story ultimately that we're going to talk about. Now this story, as we talked about in previous episode, is out of Tongji University in Shanghai, China. The headline was Naked Mole Rat's DNA could hold the key to long life.
Yeah.
And it was published in Science. And so what's the top line here about the connection between this naked mole rat and now understanding longevity generally?
Yeah. I mean, longevity is something that we've been after for a very long time. And it turns out the naked mole rat's DNA could hold a secret to how to live longer. Okay?
I told you. I told you guys.
Yeah, dude, naked mole rats are incredible animals. And we're going to get right into it, okay? So, there's a grand challenge when it comes to aging, right? And the quest for living longer. There's two main theories when it comes to aging. There's the programmed theory, which means that aging is a deliberate, genetically determined mechanism that makes us die, right? It's programmed into our genes such that the hormones kick in at a certain age. There's some internal clock that kicks in, and that sort of it's part of evolution. It's a way to make sure that no one's living too long. Okay. Then there's damage or error theories, which suggest that aging is actually just a cumulative result of environmental insults and imperfect repair. And if we were to somehow take care of those environmental factors and get rid of that imperfection in the repair of our body, then we will be able to live longer, right? And the naked mole rat discovery that we're talking about here supports the idea that longevity is actually might be an evolved trait of superior damage control. It's not a programmed thing, and actually if we could do this damage control, there could be a way for us to live a lot longer than we are right now.
Don't tell Peter Thiel.
Yeah, exactly. So, okay, there's a few hallmarks of aging that I want to talk about. This one is telomere attrition. Okay, telomeres are the protective DNA caps at the end of our chromosomes. They're a bunch of repetitive DNA that's basically nonsense. It's just there as a cap to make sure that the inner part of our chromosome gets replicated, right? Every single time there's cell division, those telomeres get shorter and shorter and shorter, okay? Because the way DNA replication works is you have DNA polymerase that goes down and then replicates, right? But the binding and unbinding of that DNA polymerase is a stochastic process. It's happening just based on some probability. And so the probability that goes all the way to the end is low, right? And that's why you have a bunch of nonsense telomeric DNA at the very end. It's just a bunch of AT, sometimes GC. I guess GC is on the other side. You get what I'm saying, right? Yes. It's just like, it's a bunch of repetitive DNA that doesn't actually code for protein. It's just there to make sure that I get everything in the middle.
Yes.
Right? So it's these caps at the very end.
Yes.
Now, short telomeres leads to cellular senescence, which is like the cell goes into a kind of coma-like state.
Okay.
And it can lead to apoptosis, which is when the cell programs its own death. Okay? And it's been shown that it's a key contributor to organismal aging. So the telomeric DNA getting shorter and shorter correlates to the organism at large getting more and more aged.
Which sort of makes sense. Like your buffers that are protecting this replication process are disappearing over time.
And like maybe you're losing genes on the ends, you know, and things like that. Yeah, there's some mechanistic view there, right?
Okay.
Now, there's another one. There's deregulated nutrient sensing. So this comes from the mTOR pathway, which is for mammalian target of rapamycin. So this is something that controls cell growth and metabolism. And sustained activation of this pathway is linked to accelerated aging.
Okay.
And you can inhibit it with a drug called rapamycin. And this you might have heard about. It's like this like de-aging drug unlocking the secrets of youth. People are taking this rapamycin. Well, it's literally targeting this pathway called mammalian target of rapamycin, mTOR, because it's literally named after the drug. Because a lot of times in biology, you find the thing that is affecting it, and then that's a good way to say the name of,
the thing.
So if you inhibit this pathway with rapamycin, it can lead to extended lifespan in various organisms.
Interesting. So there's two separate things here. There's preventing the telomeres from
from getting shorter.
From the buffer
That's
from
something
getting
that we
shorter.
might want to do.
So that's one piece. And then the other piece is there's this mTOR that accelerates aging. So if you inhibit it, then you don't have this accelerated aging.
Exactly. And then there's a third one that I want to get into, which is the role of sirtuins. They're kind of like the guardians of the genome.
Guardians of the genome.
Yeah, exactly. I love that name. They're a family of 7 mammalian proteins. They're found in mammals. They go Sirt 1 to 7, and they regulate cellular health. And what they do is they regulate the histone complexes around DNA. Histones are these proteins that wrap the DNA around themselves to create the chromosomes. You must have seen the chromosomes in these cells, which are these like bulky little things. Most of what you're seeing are actually these histone proteins. The DNA is the tiny little thread that you wouldn't actually see, but it's wrapped around these histones, right?
Okay.
And the sirtuins are the ones that regulate these histones, okay? Now, the activity of these sirtuins gets increased during caloric restriction, which has been shown to be something that can lead to less aging, right?
Okay.
If people go way ham with this and go with the intermittent fasting, where they're like, they're like not eating for like 2 days or whatever.
Yes.
Now that it's iffy there.
Okay.
Don't do too much of a good thing.
Yeah.
But caloric restriction has definitely been shown to cause very good things in terms of like de-aging. Okay. So one of the key threads in all of these is that it has to do with the genome.
Right.
Right?
Like aging, all these factors are correlated to
the genome. To the DNA.
So if we want to talk about aging, we have to talk about the genome.
Yeah, if we want to talk about aging, we want to talk about the genome. Specifically, we want to talk about genomic instability, right? The idea is the more stable your genome is, all 3 of these things that I just talked about are basically making the genome more stable. The more stable your genome is, the less aging you do, right? Genomic instability is the most fundamental driver for aging, it seems, right? Okay. And what we want to do is we want to prevent DNA damage. And if there is DNA damage, we want to repair it. Okay? The worst kind of DNA damage is something called a double-stranded break. DNA is a double strand. It's got two strands interlocked in a ladder. If you break one, it's fine because you can use the other part to sort of repair it. But if you break both, then you've effectively split the chromosome in 2, right? So that's really bad.
Yes. Not great.
It's the most catastrophic way of doing things, right? And accumulation of these unrepaired double-stranded breaks can cause cellular senescence. It can cause apoptosis. Too much of this in your body, and you're aging a lot. Okay, so the efficiency and fidelity of this double-stranded break determines your resistance to aging. And usually, what happens is, if you get a double-stranded break, remember you have 2 copies, right, in your cell of the chromosomes. Especially in the like during cell division, the cell makes 2 different copies, right? So during the S phase of your cell cycle, there's going to be 2 copies. You can use that other copy,
right,
to be like, crap, where does this fit?
Yes.
Right? And did I miss anything? Because if the 2 broke,
yes,
and some of the DNA fell off, I don't want to just like attach it and then like delete an entire gene.
Yes.
So I can get the copy from my sister chromatid, like the copy of it.
Yes.
And then I shouldn't say sister chromatid because that's the other pair. But from your homologous chromosome, which is the exact copy,
yes,
bring it over, compare the 2 strands, and then be like, oh, I'm missing an A here, a T here,
yes,
a G here. Put it all together, and then I can repair my double-stranded break.
It's like that movie with Ewan McGregor, The Island, where every human had a copy clone that was on this island. And so when you got injured as real human billionaire, they would take your copy that was on this island, and then they would take the parts they needed from the copy and then give you like an organ transplant or all this other stuff. So it was like a perfect copy of you, but the copies had no idea that they were copies. It's a whole nother story.
Holy cow.
But it's a great movie.
Dude, I gotta watch that movie.
It's a class, it's like a little bit older. But this idea that there's a reference, if you have a double-stranded break, there's still a reference that you can then rebuild that that break from that is independent of these 2 strands together.
Yeah. And you can make sure that you're not missing anything.
Right.
You didn't like staple things wrong.
Right.
You know? So that's so all of that is background about sort of what are the things,
the levers
that we can pull. Okay. And the main thing that we want to do is we want to fix DNA instability. We want to make our genome more stable. And that is where the naked mole rat comes in.
Let's go, Rufus.
Okay. Rufus comes in. The biological name is Heterocephalus glaber. It's probably the ugliest mammal I have ever seen. I'm going to be honest. Okay. We got some photos here. It's pretty bad. To be honest, I think Rufus, like they really, the cartoon guys, they deserve a raise because they made a really cute cartoon from that.
They Disney-ified
it
Rufus.
looks so bad.
They kept the teeth though.
They did. They kept the teeth. Yeah. These things are incredible though. Okay. They live in East Africa. They live in large communities, and they live for nearly 40 years. Okay. That's insane. I remember when I was in my lab at UCLA, we were doing experiments on rats. Our lab rats lived max 2-3 years, right? And that's like max, because in the wild, rats are going to live like, there's rat on rat violence, right? But they lived a pretty good life in our behavior lab. We weren't one of the other labs, let's say, but the tops 2-3 years. These guys are living 40 years.
That's actually crazy.
Right?
Yeah.
Naked mole rats live 40 years compared to 3 years for a mouse. Anything that is that size lives around 3-4 years. Dogs live only 10.
Yeah, right.
Right? These things are living 40. So clearly,
that's orders of magnitude.
Yeah, clearly they're doing something.
Yeah.
Right?
Yeah.
They're clearly they're doing something. They've evolved some potent biological mechanism that is delaying aging.
Right.
Okay? And so they've been a really great model organism to try to figure out what is going on.
Right.
Okay? They're resistant to diseases. So not only do they live long, they live really healthy lives. They don't get cancer. They don't get neurodegradation. They don't even get arthritis like every other mammal does. Right? And it suggests that the fact that they don't get these age-related ailments suggests that there's some fundamental underlying process that they're doing. They're not fixing every little thing with a custom fix. There's one underlying fix that they're doing that is sort of fixing all of the rest. Right? That's why it's so interesting, right? And
they sort of have the janitor at the school that has the admin key that unlocks all the doors.
All the doors.
You don't figure out and pick every lock on every door. You just have
you
the
just
master
have it.
key.
And for the longest time, it's been like, what is that? What is that key, right? The other really cool thing, it's very relevant to humans because their transcriptomes. The transcriptome is basically all of the mRNA that gets transcribed from the DNA, and their protein coding sequences. So the parts of the genome that actually code for the protein, those are very similar to humans, and they're more similar to humans than mice are to humans. Okay, so it increases the likelihood that whatever mechanism is happening in the naked mole rat, we could maybe translate that to human longevity.
So
studies.
we're saying that we can make Iran unstoppable. We're moving from stoppable to unstoppable.
Yeah,
I told you I'm gonna crush the impossible jokes on this one.
Yeah, that was a good one actually. So now the problem is we got to figure out what exactly is going on, right? And for the longest time, people actually thought they maybe knew what was happening, which is the C gas protein, the C gas pathway. I don't know if you remember, but this was one of my predictions for the medicine prize this year.
Yes, it
the
was.
C gas pathway.
Yes, it was.
It didn't win, but it's coming back, and maybe it's going to come back and win the Nobel, in the next few years. You can already see that it's a very big deal, okay? So the C gas protein has a primary function with innate immunity. Let's just do a little bit of review. DNA lives in the nucleus of our cells. We are eukaryotes, and so there's not going to be any DNA in the cytoplasm of the cell. Everything is going to be compartmentalized in the nucleus, which means if you ever see a DNA molecule in the cytoplasm, something has gone wrong. Either a virus has come in and infected you, or something that should have been in the nucleus has now strayed out, and the cell is straying into cancer territory or doing weird stuff, and it needs to be dealt with. Okay, so the C-gas protein, the primary function is to detect that cytoplasmic DNA, bind to it, and then catalyze some reaction that activates an inflammatory response or an antiviral response. Okay?
So it's basically looking for intruders in the cytoplasm.
Yeah.
Identifying it and then bringing in people to deal with.
Yes, yeah.
The
And those intruders are always just double-stranded DNA. If I see double-stranded DNA in the cytoplasm, you're not in the house. What are you doing out here? You know, there's a problem. Either you're from out there or you're like supposed to be in the house, right? What's going on? Now, that's great for the innate immunity part, right?
Okay.
It's detecting stuff in the cytoplasm, but it also has a paradoxical role where it starts detecting stuff in the nucleus of our cells.
Okay.
Okay. And when it does stuff in the nucleus of our cells, it can actually suppress that homologous recombination. You know, that the part I was saying where you got the double-stranded break and then the homologous chromosome comes in and then it does this whole thing. Well, during that whole part, there's going to be like a lot of naked DNA hanging out, right?
Right.
And the C-gas protein is just looking for DNA to bind to.
Right.
It's just lock and key.
Right.
Right.
So the C-gas doesn't necessarily have the like flight list of everyone who's supposed to potentially be in transit during this recombination.
Exactly.
part.
Yeah.
It's just like, if you're out here, you're a problem.
Yeah. If I see you, you're a problem. Most of the time they're hanging out in the cytoplasm, but every time they're in the nucleus, it starts getting confusing, right? Because there's a bunch of DNA in the nucleus and it's not always surrounded by histones and things like that. So the C-gas can actually inhibit that repair process. And so that's kind of weird, right? Because like you can have this. So why is it doing that? Well, it could be just an evolutionary trade-off where you've got a rapid immune response. And okay, to have the rapid immune response, maybe you do need long-term, maybe you let go of the long-term DNA efficiency, the repair efficiency.
You can't do both.
Right? You can't do both. This is already working, right? But with a mole rat, you need both because you're living that long, right?
Right.
So there was evolutionary pressure for the mole rat to fix this problem that maybe other mammals didn't have. Okay? And that's what this paper is doing. Okay? So this paper that was out in Cell, it's unraveling the naked mole rat's genetic secret. They found the C-gas mediated mechanism in that naked mole rat, and they showed why that DNA, the part of the DNA that codes for the C-gas, is different than the humans, and how that difference actually manifests within the cell.
Fascinating.
Okay, so they're actually doing that. So there's an unexpected function. The first thing they did was they used GFP, which is green fluorescent protein. It's a great tag for whenever you want to see stuff that's going on in the cell. You tag it with GFP, and what they can actually see with the GFP is this activity that's happening inside the nucleus. And what they found is when you have the naked mole rat's C-gas version versus the human version or the mouse version, the naked mole rat C-gas version had 3-fold higher concentrations during this homologous recombination than the human version.
Yes.
Okay. And so, and if you take CRISPR-Cas9 and you cut out the naked mole rat version, then those cells can no longer do this homologous recombination. So not only is the naked mole rat version not inhibiting this homologous recombination, it's actually helping. So they went in, so somehow evolution went into the naked mole rat genome and made the changes to switch the behavior of C-gas to something that was from something that was inhibiting to something that is actively helping this high fidelity DNA repair.
As independent from the job responsibility of dealing with rogue DNA within the
outside,
cytoplasm.
yes. It still does that job.
It still does that.
It still does that job, but inside the nucleus, now it's doing an additional job. It's actually helping this homologous DNA repair.
And not having this sort of conflict of it now has access to the classified
exactly.
system.
And so they did a bunch of different molecular biology techniques to pinpoint the domain of the C-gas protein that was different. Once they pinpointed the domain that was different, they went in and looked at what were the amino acids that were different. They found 16 different amino acids. Then they went in and made chimeric proteins where what you can do is you can put in this amino acid and this amino acid and see which of those, because some of those 16 might just be like random evolution type stuff.
Right.
But 4 of those 16 were specific substitutions that caused this switch. What you can do is you can take the human version and you can put in those 4 instead of our human version, and then that protein now becomes the naked mole rat version. So we've pinpointed exactly what are the genetic changes that cause this. Isn't that insane that we can actually do that, dude?
That's so unreal.
Yeah.
To think about. Down to literally the amino acid.
Yes.
Like the four individual amino acids that make the difference.
Yeah, yeah. It's insane.
And it's like a consequential difference.
Yeah. Yeah.
It's the difference between 3 to 5 years and 40.
Yeah. Exactly. Which is four. It's pretty insane. And then so now we have this difference, right, between human sea gas regulation, which what human sea gas is doing is it binds to the DNA and then it kind of prevents all of the other repair mechanisms from coming in. What the naked mole rat version is doing is it binds to the DNA and then it actively recruits all of the other chromatin binding aspects to like make this thing go faster, right? And have higher fidelity.
Instead of being an absolute firewall and blockade, it sort of basically has, it's a little porous for specific helpers that it knows are actually there to facilitate a job function.
Yeah. It's insane.
That's fascinating.
We could do this. And then the real nail in the coffin for me was like, what they did was they could now introduce the mole rat version of this gene into model organisms like the Drosophila, and the fruit flies lived longer and they were more robust and they could climb up walls faster, right? All of these assays the fruit flies were doing, right? They went to maximum lifespan in mice. The mice were living longer and they were living more healthy. And so now we start thinking, okay, what are we going to do with the humans, right? I mean, we can't genetically engineer, but what you could do is you could have there's obviously gene therapy, right? But you could always also have small molecule drugs that mimic what the naked mole rat version of the protein does. So you got the human version, right? And let's say the human version has a particular shape, and we can take a small molecular drug that binds to that human version to make it mimic the shape of the mole rat.
Yes.
Right?
Yes.
And then now it's going to do all the recruiting that the mole rat version was doing.
So it's sort of like we create a therapy that like mimics the sea gas process.
Yeah.
The 4 amino acids specifically.
Yeah, we know exactly what that difference is, right? Because we know these are the 4 amino acids. Right? Now we can start doing structural studies.
Right.
Which I'm sure is going to be next.
Right.
It's like, what is the exact structure of those 4 versus these 4?
Yes.
You know?
Yes.
Like, and how do we engineer a drug that looks exactly like that binds exactly the way I want it to, and then all of a sudden our DNA repair mechanism can be what the naked mole rat had, which is so cool.
Which is now the idea being, there are a variety of factors that impact aging, and the one that this is solving for is the sea gas, which is meant to be a protection mechanism for like rogue viral DNA being inside the cytoplasm, but then also sometimes can be inside the nucleus and doesn't have the right instructions.
Yeah.
So it can disrupt a normal process of double-stranded broken pairs needing to be repaired. That's another problem. The problem is that double-stranded break is a driver of aging.
Yeah.
And so we want to make sure that those double-stranded breaks are fixed without this sea gas interrupting it because it's trying to do another job and applying it here.
Just getting confused.
And we sort of are now like, we can just give you like 4 amino acids and now you can still do the viral cytoplasm stuff, but not just only not screw up the repair, you can actually make it more efficient.
Yeah.
That is crazy.
Yeah, dude.
That is actually crazy. And again, to understand, to be able to draw the through line through all of those things.
All of those things.
To get to that level of precision, to be able to now mimic it in naked mole rats, in fruit flies,
in mice.
Like, it's going to continue on the journey. I mean, that's,
it's working.
It's working.
Yeah.
And we've talked about longevity in a previous episode, in that, these two theories, is it error or is it pre-programmed? the fact that there's indication that it's not pre-programmed and it's because of this
And
error.
it is this error thing maybe we can mitigate.
This is just one of many avenues of attack to sort of deal with the quote-unquote aging problem.
And this might not be the only secret that the naked mole rat has, right?
It's just it's just one.
It could be as you said, the janitor with the master key, but there might be, groundskeepers with a master key as well.
Yes.
Yeah.
Yes. This is truly fascinating. This was a great series of stories this week.
Yeah.
We are starting off the fall with a bang. We hit at the top, not portable yet, but new laser plasma device that could be light enough to be used in the field. This was around muon generator and, the implications that it has for a variety of fields. That came out of Lawrence Berkeley National Lab and was published in the Physical Review, Accelerators and Beams.
Yep.
We moved on to the second story about sodium batteries. The sodium batteries, how they can be cheaper than lithium, but just as powerful, what the limitations are, where we kind of are in the frontier. Great paper out of University of Chicago and UC San Diego in Joule. There's clearly going to be pickup on that story. Yeah. There are so many incentives for a variety of nation, state, and private sector players, in addition to the academic community, to want to push that forward. And we ended with our story about Rufus out of Tongji University in Shanghai, about unlocking longer life by this key understanding from the naked mole rat DNA, which was very fascinating.
Yeah, that was cool.
Very, very fascinating. So this is the conclusion of our episode 13. My name is Lester Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary. This is From First Principles. We'll see y'all next week.